Hello, I'd like to buy a shape. I need a triangle, in particular one with a right angle, and I need the hypotenuse, that side across from the right angle, to be about this long. Great! Oh, I see you have another one like it over here, with the same hypotenuse length, but it seems to me like a bit more triangle for my money. I see you also have a third one. How many of these do you have? Infinitely many, you say. Oh boy, I'm gonna need a sec. This is a conundrum that a friend of mine encountered about a year ago, and it stuck with me for a few reasons. For starters, it's not just an abstract exercise, it actually came up while he was at work, bussing at a restaurant. They had this bin that they kept their ice cubes in, and there was a little sliding plate that sectioned off this little right triangular corner for them to keep crushed ice in. Crushing the ice to put in that corner took time, and it wasn't something they wanted to suddenly have to do during a rush, so it was pretty important to them that they had as much storage volume for the crushed ice as possible. So, since the height of ice in that corner is decided just by the bin, which isn't really something we can do anything about, our problem really just comes down to maximizing the area of this right triangle, where this plate, with some constant length, acts as our hypotenuse. We end up with an example of what we might call constrained optimization. We want to optimize the area of our triangle, but we have a constraint for how big the hypotenuse can be. There are some pretty standard ways we can answer a question like this using some calculus, which is what I did first to get my friend the answer he needed. But I got curious about if a question that could be asked using only geometry could also be answered using only geometry. That ended up leading me to some new ways to look at the problem, and as of recording this, I have 5 total types of ways that I know how to solve this problem. 2 of them use those calculus tools, and I think it'd be good to talk about them separately some other time, so that we can get into how those calculus tools function. But these 3 end up using just the tools of high school math. One of them only uses things you should know from an algebra class. That said, that was actually the last of these solutions I've found so far, and in some ways it could be considered the trickiest. Using simpler tools or calculations to solve a problem can sometimes mean needing to introduce different kinds of difficulty and complexity. Before I show these 3 pre-calculus solutions to you, I'd like to give you an opportunity to try solving the problem for yourself. If you'd rather not, that's entirely fine, but I personally did enjoy finding the solutions I did, and even if you're not confident you can solve it, trying some things out might make the solutions I show you more meaningful. But to be clear, the answer itself is not all we're looking for. My friend actually had a good idea of what triangle should be the best ahead of time, just like how some of you might have some theories. That said, he still came to me because he knew that his guess was different from knowing for sure, and what he really wanted was certainty. So, if you would like to try answering for yourself, try to make sure you leave as little doubt as possible that your answer is correct. All ready? Alright, then let's get into the first proof. One thing which is consistent across these proofs is that we need some way to uniquely describe our right triangles. For this proof, what we're going to look at is what happens when we choose the lengths of the 2 legs of the triangle, which are the sides next to the right angle. Let's call those side lengths A and B. This is helpful for us because both the area of the triangle and the length of the hypotenuse can be found if we know what A and B are. In particular, the area is equal to 1/2 A times B because we can treat B as our base and A as the altitude drawn perpendicular to that base. So this is our 1/2 base times height. The idea is essentially that the area of a triangle is half of a parallelogram, and in particular our right triangle here is half of a rectangle. To find the hypotenuse, we can use a fact about the 3 side lengths in a right triangle known as the Pythagorean theorem, named after an ancient Greek mathematician known as Pythagoras, which I should note the attribution here is a little complicated for a few reasons. Ancient history is complicated, and a lot of different civilizations came to these ideas through different means, but the Pythagorean theorem is still the broadly accepted name for it. In any case, if you're not very familiar with the theorem or would like to know why it's true, consider what happens when we arrange 4 right triangles like this, such that the sides of the triangles line up, and all the right angles point outwards. Looking at the blue sides, we end up with a big square, where each side is made up of 1 long side plus 1 short side from our identical right triangles. And in the middle, we can see that our 4 hypotenuses are also forming a quadrilateral, which we can show as a square by looking at some angle relationships in the right triangles. So, because the area of the total blue square is made up of the small gray square and the 4 right triangles, with no overlap, we can say that those smaller areas have to add up to the total area of the big square. Now, we can write out some expressions for each of these areas in terms of our side lengths of A, B, and C, which is essentially like stating how we would find the areas if we knew those lengths. The squares' areas can be found by squaring the side lengths, which means multiplying them by themselves, and the triangle's areas are still 1/2 a times b, like before. Now, a common mistake here would be to say that the sum of a plus b all squared is the same as a squared plus b squared, essentially distributing the square over the addition. That's actually not quite the case. We can pick any two non-zero numbers for a and b, like 2 and 3, and see that these two expressions have different values. Instead, in order to rewrite this, we'll have to use a process known as FOIL, which is really just using the distributive property twice. If squaring a plus b means multiplying it by itself, then notice that we're multiplying some number, a plus b, times the sum of two numbers, a plus b. So we can use the distributive property once to multiply both of those first a and b times a copy of that second parenthesized a plus b. Then, those are also products involving a sum, so we can distribute again to get each possible combination of a term from the first copy of a plus b times the second copy. Now, notice that we have these two terms where there's an a being multiplied by a b. Since multiplication is commutative, these two terms are actually the same, so we can combine them to make one 2ab term. This is the term that makes a plus b all squared not the same as a squared plus b squared. Now notice, the total area of the four triangles gives us the same 2ab on the other side. So subtracting it from both sides, we end up with the final form of the theorem, the famous a squared plus b squared equals c squared. Now in our case, if we know c is some constant, then c squared is also some other constant, so we can say that a squared plus b squared is something we have to keep constant. Now, I know we took a little while to prove how a and b are related to c, but it actually gives us a huge tip about the trick of this solution. Because, using that same FOIL method, we can also expand a minus b all squared, and it's almost the same as our a plus b squared, except when we multiplied the a times b each time, there's an extra minus sign attached, so the sign of that 2ab is different. But we know 2ab is the same as 4 of our right triangle areas, and otherwise that a squared plus b squared is just the same as our constant c squared. So if we'd like, we can rewrite that a minus b squared is the same as c squared minus 4 times the area we're trying to maximize. This relationship can also be represented with areas, just as in our Pythagorean theorem proof, if you want to keep things entirely geometric. Now, if area gets larger, that would mean we're subtracting a larger number from our c squared, which gives a smaller result. So if we want the area as large as possible, at the maximum, then this a minus b squared would have to hit its smallest possible value, which is its minimum. This ends up being a huge breakthrough for us, which we can see when we think about the results we get from multiplying some number by itself. If we look at a graph of y equals x squared, where the y values are representing the results of multiplying each x value by itself, we can see that the graph goes up whenever we move left or right from the origin. That's because if we move to the right, we'll have a positive x value, so x is greater than 0, and we can multiply an additional copy of that x on both sides of that inequality without flipping the sign. And since 0 times x is always 0, that shows us that x squared is greater than 0. In other words, a positive number times a positive number is a positive number. Similarly, moving to the left, x has to be negative, so x is less than 0, and we can multiply by x on both sides, but remember that multiplying by a negative number in an inequality flips the inequality sign. So we still have x squared being greater than 0. Negative times negative is also positive. So the only time y isn't strictly positive is right here at the origin, when x equals 0. In our case, that means a minus b all squared has to hit its minimum at 0 as well, when a minus b is 0. And since the maximum area causes a minimum for a minus b squared, that means our maximum area occurs when a equals b. From here, we could solve for expressions for a and b in terms of c, but it's enough to say that the right triangle we'd want for our solution is the isosceles right triangle, the one with two equal legs. Another way we can think about constructing our triangle is to start out with our known hypotenuse, this line segment we'll call AB. Now we can try placing a third point, C, to complete the triangle. Now, a hiccup we can encounter when we do this is that depending on where we place C, the triangle won't necessarily be a right triangle. We need this angle at C to be a right angle, and here it's not. So, in order to meet this right angle constraint, there's a certain set of points we'll have to pull C from. As it turns out, all those points for C end up tracing a circle, where our hypotenuse AB is a diameter. This is a result of a circle theorem known as Thales' theorem, named after a Greek mathematician known as Thales, although this attribution is also disputed. This isn't directly telling us that C has to lie on the circle for the angle to be a right angle, but because we can generate right triangles with any possible set of angles using the points from the circle, and having a side and two angles uniquely define the triangle, we can show that this circle gives us the set of all possible points for C. Now, since Thales' theorem is so important to the idea behind this proof, I think it'd be best to include a demonstration of how it can be proven. So, starting just from the facts that AB is a diameter, and C is some other point on the circle, we'd like to be able to show that the angle at C has to be a right angle. In order to do this, notice that A, B, and C are all on the circle. If O is the center of the circle, that means that all these points must be the same distance away from that center. That distance is the radius. If this is the case, we can think of this new radius OC as splitting our triangle into two smaller triangles, both of which are isosceles, because they have two sides which are radii. From this, we can get that the angles opposite from the congruent sides also have to be congruent. This is due to a fact known as the isosceles triangle theorem, which we can prove is true by taking a generic triangle with two congruent sides and cutting the vertex angle into two halves with this angle bisector. Now, each half of our triangle has the same pair of side lengths with the same angle between them, so they end up being congruent by the SAS congruence postulate. If you have two sides and an angle between them, then the only way to finish the triangle is to connect the two sides. So, if these two triangles are congruent, in particular one being the mirror image of the other, then these two base angles have to be congruent, as we claimed. Now, let's create some variables, alpha and beta, to refer to these two angle measures in the smaller triangles. Recall that the three angles of our triangle ABC, as with all triangles, have to add up to 180 degrees. If you don't know why this is the case, try looking at what happens if you draw a line through point C parallel to line AB. So, since angle ACB is just angles OCA and OCB added together, we can show this means that alpha plus beta equals 180 degrees. As a result, one of those copies of alpha plus beta on their own would have to be half of that 180 degrees, which is 90 degrees for a right angle. But that alpha plus beta is just the same as angle ACB again, so that means that we've shown that the result of Thales' theorem holds. And since we didn't assume anything about C except for it being on the circle, this will work for all the points on circle O, except for exactly on A and B, since there we won't really have an angle or triangles to talk about. Now, remember, our goal was to maximize the area of this triangle, which is our 1/2 basement's height. With how we have our triangle drawn, it's natural to make our hypotenuse the base, which is convenient because if the base is always the same, then all we have to do to find the maximum area is to maximize this height drawn perpendicular to the base. Now from here, you can probably stop by I where the maximum altitude occurs, but if we want to be precise, a slick idea here involves this right triangle that our altitude forms with part of our base and the radius OC. OC is the hypotenuse here, so we know that there can never be a side of the triangle longer than it. This means that the altitude is always going to have to be at most as large as the radius of the circle. From here, we can multiply both sides of this inequality by our 1/2 and our base in order to get an inequality in terms of areas, and it's clear that our area could never be larger than 1/2 times AB times OC. But since we can actually achieve that by making the radius OC perpendicular to AB, making it itself the altitude, that must be the triangle that gives us the maximum area. Now notice our two smaller triangles, AOC and BOC, both have these same radii as side lengths that we mentioned before, and they also have right angles at O, so that gives us our side angle side for SAS again. So the triangles are congruent, which means their hypotenuses also have to be congruent. This shows that our triangle ABC is once again the isosceles right triangle with the given hypotenuse. So in our last proof, we proved the isosceles triangle theorem as a subproof, which involved splitting an isosceles triangle into two congruent right triangles. But what if we did that backwards, cloning our right triangle, reflecting the clone about one of its legs, and then joining it with the original to make one big isosceles triangle? Each of our right triangles is half of the area of the big isosceles triangle, so the maximum area for the right triangle must come when the total area is maximized. We can define this new isosceles triangle as a triangle with two sides of length C, with an angle twice as large as one of the acute angles of the original triangle. Remember, SAS, so two sides and an angle between them, is enough to uniquely define our triangle, so it also has to be enough to determine the area. To see how, let's make it a bit clearer that we're using one of these C's as our base, and then remember that we just need to find an altitude drawn perpendicular to that base. Now, notice this right triangle that the altitude just completed. We know two of the angles, so that has to be enough to know about the ratios in this triangle, since any other triangle with a right angle and an angle of 2 theta would have to be similar to this one by AA similarity. In particular, with this being a right triangle, we have special trigonometric functions called sine, cosine, and tangent, which can tell us these ratios if we plug in that non-right angle we know, the 2 theta. Here, we want to know about the side opposite from the 2 theta angle, and we know about the hypotenuse, so we'll want to use the ratio between the opposite side and the hypotenuse. That ends up being what we call sine. So, if sine of 2 theta is our altitude divided by c, then the altitude is c times sine of 2 theta. Now, using area equals 1/2 base times height again, here we have that the area is 1/2 times c squared times sine of 2 theta. In this case, we know c is a constant, so if we want this total area to be maximized, we'll have to maximize the sine 2 theta term. In order to see where sine of 2 theta gets its maximum, it might help to look at what we call the unit circle. This is a circle with radius 1, and for each point on it, we can think about generating a right triangle by letting the radius out to that point be the hypotenuse, and the distances right and up from the origin be the legs. If we define our angle of interest 2 theta as this angle at the origin, then once again we have a triangle we can solve with our trigonometric ratios. The horizontal side is adjacent to the angle, so we can find it using cosine of 2 theta, and the vertical side is opposite from the angle, so we can find it using sine of 2 theta. So now we need to find the highest point on the circle, which might sound familiar, because we've actually wrapped back around to the second proof again, where this sine of 2 theta idea was lurking if we wanted to find the expression for its altitude. The 2 theta here comes from a theorem known as the inscribed angle theorem, which relates this central angle to an angle on the edge of the circle. In any case, once again, the highest point is at the very top, where our entire 1 unit's worth of radius is going straight on the vertical, which is at a right angle to the horizontal. So, 2 theta equals 90 degrees, which means that theta equals 45 degrees. Now, recalling that theta refers back to one of the angles of the original right triangle, and the angles of a triangle have to add up to 180 degrees, once again we have to have a 45-45-90 triangle, or the isosceles right triangle. Now, some of you might have had another solution where you write the legs of the original triangle in terms of c and theta, and you end up with the sine theta cosine theta term, which you can deal with in a few ways, including with the double angle identity for sine. That's also a great way to go about things. But notice that here, if we recall that the area of our isosceles triangle is double that of the original right triangle, then dividing on both sides by this 1/2 c squared, we actually get to prove the double angle identity, sine 2 theta equals 2 sine theta cosine theta. And it turns out that trying to replicate this setup with 2 triangles back to back can end up leading you to the general proof of the sine angle sum theorem. Even after seeing the proofs, I expect a few of you have 2 particular questions in mind. How did I know to take those steps to solve the problem? And if some of you could figure out what the answer was without all those steps, why should we bother? These are good questions, but I think there's also a sense in which they miss the point slightly. If we look back at our 3 solutions, there are a few similarities in terms of how they operate. They all start by thinking about a specific way that we can set up our triangle, either by defining the legs first and working from there, or by thinking about what point would need to be added to the existing hypotenuse to complete the triangle, or by thinking of our triangle as half of a larger triangle. These are all sort of setup ideas, and they're the most unprompted, possibly seeming like they appear from nowhere, so I can understand why you might ask how I knew they'd lead to a solution. But the thing is, very often I don't. I just know that if I take our problem and just stare at it until I figure everything out, I'm probably not going to get very far very fast. So I need a step like this to break the problem down into pieces I can start playing around with. None of these setup steps are more correct than any of the others, and even if you find one that doesn't particularly help find a solution, you can always pivot to trying another one. The playing part of the solution comes in with these theorems we were using, like the Pythagorean theorem or Thales' theorem. We used these to answer questions about how different quantities in the setup were related to each other, or to find certain pieces of the setup that were hidden, like the circle in the geometry proof. Those relationships ended up giving us a way to get from the setup to something that we had a better idea of how to optimize, breaking the problem down into a simpler problem. You might also find this kind of use of these theorems confusing if you're used to thinking of them in the context of smaller problems, where they might be used in one of a few ways as explicit steps in calculations. These sorts of example problems can be very helpful as teaching tools because they're pretty simple and they can isolate a specific fact very easily, and they also tend to show very common cases where we use those facts. That said, they can also come with the downside that students get used to seeing problems set up in those specific ways, memorizing the exact way to get the answer given those numbers, and they don't end up with a clear view of the rule as a whole. Ultimately, these facts we're using aren't just specific steps in specific calculations, they're more like rules that always have to be true, which we can take advantage of in multiple ways. And there are specific reasons why we know they always have to be true, which we can show with those proofs we got into for the Pythagorean theorem or Thales' theorem. This leads into the answer for the second question as well. Some of you may have guessed, like my friend did, that a 45-90-45 triangle just had to be right, either due to symmetry or just because it looks right. But this approach doesn't do much to explain why that solution should actually be true, and there are a lot of things in math and science that just look true while actually not being correct. So this leaves a lot of room for reasonable doubt. Ultimately, higher math is not about taking things at face value, or just memorizing formulas that give specific answers to specific calculations. Higher math is about a system of logic that lets us know our answer has to be right, and why it has to be right. And if we dig into those whys, we can even know why it has to be right. Sometimes it's true that there are truths which are too complicated to get into without learning other facts first. But except for a few very basic definitions, it's never true that something in math is true just because it is, or just because someone says so. So, if you ever find yourself in a situation like my friend was, with an idea about how something works that you can't quite prove, never feel discouraged from asking why it works that way. That criticality is what math and science are all about.